The F-35 Lightning II dominates headlines as the pinnacle of stealth technology, but this narrative obscures a fundamental engineering reality. Modern air superiority isn't determined by invisibility alone. It's shaped by the mechanical trade-offs between stealth, payload capacity, operational costs, and maintenance footprint. While fifth-generation marketing emphasizes radar cross-section reduction, the actual performance equation reveals that different mission profiles demand fundamentally different engineering priorities. Consider the operational mathematics. The F-35's stealth capabilities come at the cost of internal weapons bay limitations and maintenance complexity that requires specialized facilities. Meanwhile, platforms like the JAS-39 Gripen achieve mission effectiveness through operational flexibility and cost efficiency, operating from highway strips with minimal ground support. The F-15EX prioritizes raw payload and speed over stealth, carrying twice the ordnance of stealth platforms while maintaining Mach 2.5 capability. These aren't inferior designs, they're optimized for different strategic constraints. The evidence extends beyond current platforms to prototype lessons. The YF-23's superior stealth lost to the F-22's maneuverability priorities. The X-32's unification strategy failed against the F-35's mission-specific optimization. Each decision reveals that air superiority depends on matching platform capabilities to operational requirements, not pursuing a single dominant characteristic. The question isn't which fighter is objectively best, but which design philosophy aligns with specific strategic needs. Many perceive fighter superiority as solely defined by stealth, but the F-35 Lightning II reveals a more intricate reality. Air dominance stems from a deeply integrated system of capabilities, not just invisibility. This fifth-generation American multi-role fighter, developed by Lockheed Martin, stands as the global benchmark for systemic aerial warfare, embodying a complex interplay of advanced technology and operational doctrine. Its core strength lies in its sophisticated stealth technology, which significantly reduces radar detectability, allowing it to operate within contested airspace with a heightened degree of impunity. Beyond this, the F-35 integrates an active electronically scanned array, or AESA, radar system. This advanced radar provides unparalleled long-range detection, tracking, and targeting capabilities, enabling pilots to identify threats and share critical battlefield information far more effectively than previous generations. The performance implications of this integration are profound. The F-35 isn't merely a fast jet, it functions as a flying command and control node. Its advanced avionics and data fusion capabilities combine sensor inputs from its own systems and networked assets, creating a comprehensive, real-time operational picture for the pilot. This allows for superior situational awareness and the ability to coordinate seamlessly with other units, transforming individual aircraft into a cohesive, distributed combat system. Available in 3 distinct versions: the F-35A for conventional runways, the F-35B with vertical takeoff and landing capability, and the F-35C optimized for carrier operations. Its design ensures adaptability across diverse operational environments. Practically, the F-35's value proposition extends beyond its individual performance metrics. It represents a technological leap, offering a significant advantage over older types like the F-16 and Su-27, and is considered one of the most powerful fifth-generation fighters worldwide. Its widespread adoption by numerous countries, including the USA, UK, and Japan, underscores its role as a cornerstone of Allied air power, facilitating interoperability and standardized training. However, this systemic capability comes with its own set of trade-offs, including substantial unit costs, software development delays, and notable maintenance complexity, presenting a challenge for sustained, widespread deployment. The JAS-39 Gripen operates from a fundamentally different design philosophy than stealth-centric platforms. This Swedish multi-role fighter weighs just 8 tons, with a 15-meter length and 8.5-meter wingspan, making it one of the lightest 4th-and-a-half-generation fighters in service. Its compact dimensions enable operation from short runways, including public roads, while maintaining Mach 2 capability and a 1,500-kilometer operational range. The aircraft integrates AESA radar technology and advanced avionics systems within this smaller airframe, proving that sophisticated capability doesn't require massive scale. The performance implications center on operational flexibility rather than raw power projection. Where the F-35 demands extensive ground infrastructure and specialized maintenance facilities, the Gripen can deploy from dispersed locations with minimal support equipment. This design approach reduces the logistical footprint significantly, while maintaining modern combat effectiveness through its wide armament integration capability and advanced sensor systems. The single-engine configuration, while creating vulnerability compared to twin-engine designs, contributes directly to lower fuel consumption and reduced maintenance complexity. Its operational cost structure runs substantially below competing platforms in the same capability tier. Practically, the Gripen represents the efficiency-first alternative for air forces prioritizing sustainable operations over maximum individual aircraft capability. Countries like Hungary, South Africa, Brazil, and Thailand have adopted the platform specifically because its $40 to $60 million unit cost and low maintenance requirements align with realistic defense budgets. The Gripen NG variant, which entered Brazilian Air Force service in 2020, demonstrates how this approach scales internationally. For nations requiring credible air defense without the massive infrastructure investment demanded by fifth-generation platforms, the Gripen provides a proven pathway to modern combat capability. Its ability to operate from public roads offers strategic dispersal advantages that even more advanced fighters cannot match, making it particularly valuable for countries facing potential airfield targeting scenarios. The F-15EX Eagle II represents Boeing's answer to a fundamental question. Can legacy airframe design compete with fifth-generation platforms through advanced electronics and raw capacity? This latest evolution of the F-15 platform, which entered U.S. Air Force service in 2024, achieves Mach 2.5 speed while integrating AESA radar systems and modern avionics into a proven twin-engine configuration that has operated since the 1970s. The performance implications reveal a deliberate trade-off between stealth and payload capacity. Where the F-35 carries internal weapons to maintain its radar signature profile, the F-15EX maximizes external hardpoints for substantially larger weapon loads. Its twin Pratt & Whitney engines provide the thrust-to-weight ratio necessary for air superiority maneuvers, while supporting the additional mass of expanded armament configurations. The large radar signature that compromises stealth operations simultaneously enables the aircraft to carry detection and engagement systems that smaller platforms cannot accommodate. This creates operational scenarios where the F-15EX can engage targets at extended ranges before stealth aircraft can close to effective firing positions. The advanced avionics package transforms the legacy airframe into a modern combat system without requiring entirely new production infrastructure. Boeing leveraged existing manufacturing capabilities while upgrading electronic warfare systems, targeting pods, and sensor integration to current standards. The result maintains the reliability record of earlier F-15 variants while providing compatibility with contemporary weapon systems and network-centric warfare protocols. Practically, the F-15EX serves as the high-capacity complement to stealth platforms rather than their replacement. The U.S. Air Force selected this approach specifically to address scenarios requiring sustained air superiority operations, where payload volume and operational persistence outweigh first-strike stealth advantages. At $90 to $110 million per unit, The platform costs significantly less than fifth-generation alternatives, while delivering immediate capability to replace aging F-15 Charlie aircraft. For air forces requiring proven air-to-air performance with maximum weapon flexibility, the Eagle II demonstrates how legacy design evolution can maintain relevance against more technologically advanced competitors through focused capability enhancement rather than comprehensive redesign. The Chengdu J-20 Mighty Dragon represents a profound geopolitical capability shift, signaling China's emergence as a formidable competitor in fifth-generation air power. This twin-engine fighter, developed by Chengdu Aerospace Corporation, directly responds to American stealth aircraft, fundamentally altering strategic calculations. Its design prioritizes stealth technology for reduced radar detectability, complemented by an advanced AESA radar system that ensures excellent detection and tracking capabilities across various operational environments. Performance-wise, the J-20 is engineered for air interception and superiority, especially under challenging conditions. Its aerodynamic configuration contributes to excellent maneuverability, a critical attribute for high-stakes aerial engagements. While initial production models relied on Russian AL-31 engines, China is now transitioning to domestically produced WS-15 engines, aiming to enhance performance and ensure self-sufficiency. This engine development is crucial for realizing the J-20's full potential, including its stated top speed of Mach 2, or 2,450 kilometers per hour, and a substantial range of 2,000 kilometers. The practical value of the J-20 extends beyond its technical specifications. It is a critical element of the Chinese Air Force, designed for both air superiority and ground target engagement. Its entry into service in 2017 signifies China's commitment to indigenous advanced military aviation and its ambition to project power. The J-20's presence compels global powers to reevaluate their defense strategies, as it represents a credible strategic counter to established Western air forces, even without a proven combat record. This aircraft embodies a direct challenge to the previous unipolar dominance in advanced fighter technology. The Northrop YF-23 Black Widow II represents the most significant design path not taken in modern aviation history. Developed as a direct competitor to the Lockheed Martin YF-22 during the Advanced Tactical Fighter program of the late 80s, this aircraft prioritized radical stealth and aerodynamic efficiency over the more conservative multi-role approach that eventually defined the F-22 Raptor. Its design featured a unique diamond wing configuration and an elongated, flattened fuselage that prioritized low observable characteristics above all other metrics. In terms of performance, the YF-23 demonstrated superior stealth capabilities and higher top-end speed compared to its rival. The aircraft utilized advanced heat shielding and innovative exhaust management to minimize its infrared signature, a persistent challenge for fifth-generation platforms. While the YF-23 was arguably more capable in pure air-to-air stealth penetration, it sacrificed the extreme high-alpha maneuverability provided by the thrust-vectoring engines found on the YF-22. The prototype's flight control systems were highly sophisticated for the era, yet they represented a level of experimental complexity that the United States Air Force viewed with caution during a period of tightening defense budgets. The practical value of the YF-23 today is purely forensic. It serves as a definitive case study on why the best-performing machine on paper does not always secure a production contract. The competition was ultimately decided by the Air Force's greater institutional trust in the manufacturing and production capabilities of the Lockheed Martin and Pratt & Whitney partnership. The YF-23 remains a testament to the trade-off between raw, bleeding-edge performance and the logistical realities of enterprise-level manufacturing. By choosing the YF-22, the military opted for a design philosophy that favored a more balanced, manageable risk profile over the YF-23's uncompromising pursuit of stealth. This decision fundamentally shaped the next 30 years of American air superiority, leaving the Black Widow II as a technological ghost, a reminder that in military procurement, organizational confidence often carries as much weight as the engineering specifications themselves. This historical pivot point provides the necessary context for understanding the modular, iterative development strategies that define modern fighter programs like the South Korean KF-21. The forensic lessons from prototypes like the YF-23 directly inform the modular development strategies seen in modern programs, exemplified by the South Korean KF-21 Boramae. This indigenous multi-role fighter, classified as a 4.5 generation aircraft, represents a deliberate growth approach to advanced air power. Built by Korea Aerospace Industries with Indonesian cooperation, the KF-21 aims to bridge the gap between 4th and 5th generation capabilities, emphasizing upgradability over immediate full-spectrum stealth. The Boramae, despite its visual similarity to a smaller F-22, currently lacks the full stealth features of true 5th generation platforms. Its initial design carries armament externally, a key differentiator from stealth aircraft that conceal weapons in internal bays. Powering this platform are two General Electric engines, contributing to its 12-ton empty weight and 7.5-ton armament capacity. The program has demonstrated rapid progress, with its first flight occurring in 2022 and serial production planned for 2026. This quick turnaround highlights a focus on fielding a capable aircraft swiftly, with future iterations designed to incorporate enlarged fuselages for internal weapons, thus enhancing stealth characteristics incrementally. The practical value of the KF-21 lies in its strategic flexibility and cost-effectiveness. For nations unable or unwilling to invest fully in the most expensive 5th-generation fighters, the Boramae offers a sovereign, adaptable solution. Its modular design allows for phased capability upgrades, enabling operators to acquire advanced features as technology matures and budgets allow, rather than committing to a fixed, high-cost configuration up front. This approach mitigates the financial and logistical burdens associated with cutting-edge platforms, providing a pathway to advanced air superiority that balances indigenous control, operational needs, and long-term economic sustainability. The Sukhoi Su-57 Felon serves as the primary Russian attempt to secure 5th-generation air superiority, yet it remains a case study in the friction between ambitious design goals and the harsh realities of industrial scaling. While the airframe integrates advanced stealth technology for reduced radar cross-section and utilizes sophisticated active electronically scanned array radar systems for multi-target engagement, its operational footprint is defined by significant manufacturing bottlenecks. The aircraft features twin engines capable of thrust vectoring, a mechanical choice intended to provide extreme agility in complex combat environments, theoretically allowing it to compete with Western platforms like the F-22 Raptor. However, the transition from prototype to a fully fielded, reliable fleet has been hampered by persistent engine development delays and limited production capacity. The performance implications of these technical hurdles are stark. Although the Felon is designed to operate in high-threat, contested airspace, its actual combat utility is constrained by the small number of airframes currently in service. The reliance on complex, high-maintenance systems, coupled with questions regarding the true effectiveness of its stealth coatings and radar-absorbent materials, suggests a platform that struggles to match the systemic reliability of its Western counterparts. While the Su-57 can theoretically carry a wide range of air-to-air and air-to-ground munitions,
The inability to produce these aircraft in significant numbers limits their impact on strategic theater-level operations. The gap between the design's stated capabilities and its actual deployment frequency highlights the difficulty of maintaining a cutting-edge fifth-generation program without a robust, high-volume industrial base. In practice, the Su-57 represents a high-risk, high-complexity investment. For the Russian military,
the platform serves as a necessary prestige asset and a testbed for future aerospace technologies. Yet it currently lacks the operational maturity required for sustained, large-scale deployment. The Felon demonstrates that even a highly capable airframe cannot overcome the logistical reality of slow, small-scale production. As a result, its value remains localized to niche combat roles, rather than functioning as a decisive fleet-wide force multiplier. This complexity to fielding gap serves as a forensic warning that the true measure of a combat aircraft is not found in its top-tier specifications, but in the industrial capacity to sustain its performance in the field. The Boeing X-32 was designed around a single ambitious premise: complete unification of three distinct military variants under one airframe. Unlike its competitor, the X-35, Boeing's approach prioritized shared components and manufacturing processes across Air Force, Navy, and Marine Corps requirements. The X-32 featured a delta wing configuration with a large integrated air intake that could theoretically accommodate the different thrust requirements for conventional takeoff, carrier operations, and vertical landing capabilities. This unification strategy was intended to drive down per-unit costs through economies of scale and simplified logistics chains. The performance implications of this design philosophy proved fatal to the program. The X-32's emphasis on commonality created significant compromises in each variant's specialized performance. The large intake, while suitable for the lift fan system required for Marine Corps operations, generated substantial drag penalties for the Air Force and Navy versions. Flight testing revealed that the aircraft struggled to meet speed and maneuverability requirements, particularly in air-to-air combat scenarios. The delta wing configuration, chosen to accommodate the shared structural demands of all three services, lacked the agility needed for dogfighting and imposed limitations on carrier approach characteristics. Most critically, the X-32's weight distribution and center of gravity issues made it difficult to optimize for any single mission profile, resulting in a platform that was adequate for none of its intended roles. In practice, the X-32 demonstrates the hidden cost of over-unification in military aircraft design. While the concept of shared components and streamlined production appeared economically attractive, the engineering reality revealed that attempting to satisfy fundamentally different operational requirements within a single airframe creates performance penalties that outweigh the cost savings. The program's loss to the F-35 in late 2001 highlighted that successful military aircraft require careful balance between commonality and mission-specific optimization. The X-32's failure serves as a forensic lesson that true cost-effectiveness comes not from forcing unification at any price, but from identifying the optimal level of commonality that preserves each variant's core performance requirements. This principle remains relevant as future programs evaluate the trade-offs between standardization and specialized capability. The evidence reveals a clear verdict. The best fighter aircraft is determined by operational constraints, not generation labels or marketing hierarchies. Stealth dominance dissolves when missions require maximum payload delivery. Cost efficiency trumps advanced capabilities when operational budgets demand sustainable deployment. Maintenance complexity becomes the limiting factor when forward basing requires minimal infrastructure. The F-35's stealth integration represents one valid solution to specific strategic requirements. The Gripen's operational flexibility solves different constraints equally well. The F-15EX's payload capacity addresses missions where stealth provides no advantage. Even prototype failures like the F-15EX and X-32 offer forensic lessons about design trade-offs that continue shaping current programs. The fundamental insight isn't that one platform dominates all others. It's that air superiority emerges from matching engineering priorities to mission requirements. The next time someone claims definitive fighter superiority, ask which operational constraint they're solving. That question reveals the actual performance equation.